Okay, let's got some more tips for us about verifying identities. Um, when we're working with verifying identities, we want to substitute basic trig identities. That's sine, cosine, tangent, cosecant, secant, and cotangent into the expression. We want to change those in and out as much as we can to try to. Really, what you're trying to get down to is you would like everything to be sine and cosine only, because it all comes back to those two. And if you can get it that way, it's awesome. Um, you might need to do some factoring. That's where the perfect square and the difference of squares patterns come in. Um, you might need to multiply by things like multiplying by conjugates, or even just by a sign. Man, I really wish I was a sine squared. Well, multiply everything by sine and see what happens. So you're going to have to do a lot of multiplying with just lots of different things, but it's multiplying or dividing that you're really working with there. It's really important to remember that there's a question mark over these equal signs because you're verifying it. It's not true until you verified it. So you never work on both sides of the equation at the same time. You can't add 1 to both sides of the equation because you don't know that both sides of the equation are equal. So adding 1 doesn't keep it equal, and it's an invalid move. This is the where, let's say you've got some object you're working on here and you think it equals something else, right? We're trying to verify that. Well, this is the technique where you're working with both sides where you might end up working from end to end, right? Before we just pick the more complex side and worked it until the end. Now you might be working end to end. Like I might do a couple steps down here with the red and not really know where I'm going, and then do a couple steps up with the blue and then realize, oh, wait a second, I got the same thing in this region right there. So now I know my path is this way. So there's a little bit of flexibility to this one, but you have to remember that you don't know that they're true until you've shown that they're true. Okay. Example 3. Verify by transforming each side. So we're trying to verify that 1 minus the tangent to the fourth power theta equals 2 times the secant squared theta minus the secant fourth power. Ooh, okay. There's also another thing that they didn't mention in there, substitution. If you remember way back in the quadratics chapter, we learned how to deal with something um, like a quartic function by saying, hey, let u equal x squared, and then we have u squared plus 2u plus 1, and then we could factor it, u plus 1 squared. Now, but I know u is x squared, so then I plug it in, and now I just have two quadratics that I can then solve. Okay, so that substitution process is probably going to be helpful on this problem. And the only reason why I say that is because I see those fourth degrees. So that tells me I'm probably going to have to substitute and try to make a quadratic out of something here. So, and I notice I've got a bunch of secants everywhere. You know what? I'll just leave that highlighted. I don't care. We've got a bunch of secants here. So I want to kind of see what the relationship between tangent and secant is. But, wait a second. 1 minus tangent to the fourth is really 1 squared minus tangent squared theta squared. There's a perfect square pattern. So a perfect square pattern is going to turn this into 1 plus tangent squared theta times 1 minus tangent squared theta. And then I look back at my trig identities and I see tangent theta plus 1. I'll use a different one. Tangent theta plus 1 is equal to secant squared. So now I have a secant squared theta times 1 minus tangent squared theta. Ooh, that's looking pretty good there. I'm getting closer, but I still got that fourth power thing over there. How am I going to have to deal with that? Let's see here. Looking at my little formulas up on the board. And well, you know what? Let me write down that identity that we were just working with. We were just working with 1 plus tangent squared of theta equals the secant squared of theta, right? Well, I still have a tangent squared here and a tangent squared here. So it could be tangent squared theta equals secant squared theta minus 1 in for that spot. So let me do that. Secant squared minus 1. Ooh, okay. Now when I do that, I end up with secant squared theta 1 minus negative 1 would be 2 plus secant squared. Oops, forgot my plus sign in there. And the reason why that's important is I see my 2 up there. Oh, let me not do green because I've already used green. Let's do blue here. I got a 2 and I know I need a 2 somewhere along the way, so there it is. And here's the other thing I notice. When I multiply secant squared and secant squared, I get secant to the fourth. Ah, okay. So now let me distribute that. Secant squared times 2 is 2 times the secant squared, theta. And secant squared times secant to the fourth is... Wait a second. Oh, I forgot to distribute the negative sign in there. Because I was about to get positive secant to the fourth, and that was going to be off, right? That didn't match up. So then that made me think, okay, well, maybe I just missed a sign somewhere along the way. And I'll highlight where it was. We have 1 minus tangent squared, so it's minus secant squared. So this should be minus secant squared. And secant squared times negative secant squared is minus. And now it matches. Now it's verified.